like in our day-to-day machine learning, deep learning practices and also work, we heavily utilize, I would say, like exploit these mini batch learning rates, mini batch learning rate schedulers. These terms we use in our code also. In this after this presentation, you will understand why this is so important, and from now on make it a like a habit of checking these small things in order to get your model performance, uh, like why, and also sort of understand why your model is not performing. Instead of just changing your model, changing the optimizer, changing the model structure, the neural network structure properly, without randomly changing it, there are certain things, small things that actually hamper your overall neural network performance, so to say. So the overall outline, I first introduce you why this is important, then go over to the learning rate scheduling, very brief about mini batch, then the different types of learning rate schedulers, then a practical implementation. I tried to showcase you why this, how empirically how these learning rate schedulers, especially the learning rates, which method actually impacts on your model training phase. Also your response provides better performance of your neural network, common pitfalls and how to avoid, uh, like then choosing your right scheduler, and then beyond basics, some of the techniques, those who are interested in research, digging into much more details about what is the current state of the art research work that is happening, especially for this topic, learning rate scheduler, mini batch learning rate schedulers, and then in the end, summary and the suggestions, like what you should do in your day-to-day machine learning, deep learning model development. This is me. uh, like I do work on, like, my research interest on federated learning, as Professor Priyanka already mentioned. I also mentioned, like, I do work on effective computing, explainable AI. Currently, I'm exploring. Also, I like, other than this research, I'm also interested in product design, product interest, like AI POC, product interest. So those who are interested, if you are interested in developing a product that, so to say, like, once three such example that I am currently working on: federated learning platform, explainable AI as a service, physiological data streaming platform. So if you are, if some those who are interested, feel free to reach out to me. This is my website and also my GitHub. All the codes and everything day to day I post on GitHub, so please do check. And if you feel any thing that, like, any repository that is necessary or fruitful for you, please feel free to utilize it. So let's begin. So we are in in the current era, everybody is doing AI, especially the deep learning, machine learning, especially if I like exclude the traditional machine learning solutions. Rather, I would say, like, if we, like, if the intelligent algorithm that we are trying to develop from the data is neural network based, heavily we utilize in the deep neural network, deep learning based, we utilize neural networks heavily. So in order to develop a intelligent algorithm, what or intelligent model, intelligent approach, like, you can call, you can name it as you want. So what are the ingredients? The main ingredients that you need is data, the neural network model or the architecture, and the optimization algorithm. Data is the fuel for, like, the model that we are going to develop, because it's deep learning, machine learning, all these are data driven. The network is, so to say, like, within which we it automatically extracts the information and store it. Later on, we ask questions, it answers. An optimization algorithm, it's the, like, so to say, the teacher, I would say, which actually trains the neural network, or optimizes, reduces the error of the neural network by improving the accuracy. Now, if we focus on, let's say, optimization algorithm, because this is a crucial part, the teacher, we're focusing on the teacher. If we focus, what are the main ingredients that that is needed for an within an optimization algorithm? We need the gradient information, as you see here, the direction and the rate of change of the loss function. As you see, the gradient, the loss with respect to the W are the weights, and then the initial weight and the change towards the global minimum, because our main objective is to reduce the error. And then we need the learning rates, which controls how big or how small the optimizer is going to take the steps. And then the update rule. The update rules are the formula that we use, like WT plus 1 is the next W for iteration T plus the next iteration with is equal to, that's like the formula. It's popularly known as gradient descent. WT plus 1 is equal to WT minus eta. Del W is the gradient and the loss with respect to the loss. So this is the formula that we use in our deep learning, machine learning, especially the neural network, like multi-layer feed-forward neural network, three-layer feed-forward or multi-layer perceptron, and heavily utilized in deep neural network to optimize. So these are the three ingredients, I would say, or the three major components that are necessary within a optimizer. Now let's focus on the learning rate. Why this learning rate is so much important? Because it's, in the end, the learning rate is a hyperparameter, okay, that controls how much the model weights will be changed or adjusted while training. As you can see, like if you, on the right hand side here, we have like if we visualize the loss function in 3D, we get like weight based on the weight, bias, and the dimension. In 3D, we get like the error like the landscape of the error function will look like this. You have local minima, you have the global minima. What's the optimizer's goal? You can start from any point, like here, here, wherever you want, and the starting point actually like how can you decide like where to, from where to start? That depends on initialization. In neural network, we initialize the neural network, and that's the starting point. Either it could start from here, or here. The main goal is to reach to the minimum, but the problem is like the LR, the learning rate, actually controls each step. So small step or larger step. The problem is, like, if it's too slow, consider this learning rate or and this optimization problem is equal to, like, if I explain you in layman term, is like you are asked, or you are asking a student to read a book about a particular topic or a subject, let's say neural especially AI. So too slow learning rate is equal to too slow learning pace, or learning rate is equal to longer training time. Meaning, if let's say the student, or let's say if you are if you are reading one sentence a day, meaning your main objective is to understand the book, the overall concept, and also finish the book. So if your learning rate is too slow, meaning let's say one paragraph, one sentence, or one sentence a day, that will be a bit problematic. Meaning, to finish the whole book, it will be longer. Similarly, if you go too fast, let's say you start from chapter 1, then move to chapter 5, then move to chapter 11, and then end. Meaning, it you will not understand the overall concept or overall idea properly. And that's where this convergence speed, actually learning rate controls this one, convergence speed. Too slow, meaning longer training time. Too fast, instability or divergence. It actually, the training stability, meaning we need, whenever we design, like whenever we train the neural network, it's always a balance between exploration and exploitation. The more you explore, and then like first you explore the overall landscape to understand the landscape, and then exploit, meaning fine tune the neural network in order to reach to the global minima, which is here. Okay. Now training stability is like poor learning rate actually helps to escape the poor local minima and saddle points. So what are the saddle points here? The local minima. And final, it actually controls how your model is going to explore and exploit. And that has a direct impact on underfitting or overfitting. Meaning, if if we come to the book example, like if you are asked to read, so if you jump from chapter 1 to chapter 5 to chapter 7 and then end, meaning you will know something, but the overall depth of your knowledge from that particular book will be less, meaning you are underfitted. And overfitting is like if you, let's say you've one sentence a day, you might remember the whole book sentence by sentence, all like how can I say, like a holistic scenario, a best case scenario is like you will remember everything. That happens actually in neural networks. So too slow, it remembers, it overfits. And that is why these learning rates are very, very crucial, and it has bigger impact on your model development. So what's the problem? Because now we are in a point, we have to decide what learning rate, or how can we decide a particular proper learning rate or proper learning pace, I would say. And it's quite challenging, and it's always trial and error. So how can we come up with a plan in order to set these learning rates automatically, or like a mathematical approach which automates or tells us, okay, this is the neural network, this is the data, this would be the learning rate, the optimal learning rate. So the model actually balances between the exploration and exploitation. What's the solution? The first idea could be like try a lot of different learning rates and see what works. Meaning, let's say normally the learning rates are set in between 0 to 1. Okay, in order to avoid the exploding gradient problem. Now you can do this approach would be like a brute force method. You can, let's say in 0 to 1 there will be infinite numbers. You can take some, you try iteration based, and then you see you prepare a plot and learning rate these and and check how the network actually performs on each of, and then you pick the maximum, and you can say like this is the learning rate, optimal learning rate for this approach, for this data, for this neural network, and etc etc. But it's very time consuming and it's problematic. Okay, because you like best case scenario, you may find like couple of iteration, you find your optimal learning rate and you are good to go. But worst case scenario, you may not find it. So what's the next idea that we can propose? And it's very time consuming. The next idea is do something smarter. Come up with a adaptive or like a learning rate that adapts to the landscape. Remind the landscape, like the 3D landscape, local minima, the global minima, and different plateau and everything. So what if the learning rate or like that learning rate can be adapted based on the landscape? Yeah, that could be the idea. Let's explore it. So we're focusing on idea 2 because that seems more interesting. So either we can go for a decay based or like adaptive learning rate based one. what it solves like, now the learning rate is no longer fixed. We can use like we can change, make it bigger when we need, smaller when we need, and it based on how large the gradient is, how fast the learning is happening, and size of particular weights and different parameters. It depends on like who developed and based on what you want to develop. Okay, it's an open research. All these parameters, which are the parameters that you can consider in order to adjust your learning rate. Let's say either it's a decay or adaptive one, but making it larger, making it smaller. So from this figure, you can see like if it is too slow, it takes small steps and will be like, in order to reach to the minimal point, it will be like very, the overall process and the time will be very long. Too high is it jumps from one point to another point. May there is a possibility that it skips the like it never reaches to the global minima. The perfect is like whenever you need to explore, you can take bigger steps. When we need to exploit, meaning fine tune the network, you can reduce your step size or learning rates. That's the like optimal or just right approach. Now, in order to set that learning rate properly, we often use in like in our day-to-day deep learning libraries, like either in TensorFlow or PyTorch, we utilize, or this term comes up, a learning rate scheduler. It's like a algorithm or a function that actually sets your learning rate based on couple of based on those matrices that I already mentioned, like the gradient, how far the gradients are, then the step size and all this stuff. Why this learning rate? Because now we need a like in order to adjust or adapt the learning rate based on the uh, landscape of the error function, we need these particular learning rate schedulers which automatically schedules. Higher learning rate actually helps on model quickly learn or explore the overall concept, and lower learning rates support fine tuning and stability. So sometimes we take the bigger steps in order to explore the whole uh, landscape, and then small steps to reach to the global minima. So this learning rate actually aims faster learning in the early stages, fine tune later, helps model to escape saddle points or sharp minima, local minima points, and it aligns with the training progress and gradient noise, which later part we will explore different learning rate schedulers, which actually like adapts the training process progress and gradient noise. Now, before diving into deeper concepts, let's just like understand like the mini batch approach. It's a the mini batch, the name actually suggests you have, let's say, a huge amount of data. The mini batches are a subset of the whole data, okay, and which actually use in order to train or train or optimize your neural network. Okay, so the popularly known is the batch gradient one. This particular approach actually uses the entire data set. It's stable convergence, but memory extensive, because if your data is too large, in order to fit to the memory, you need bigger memory size, RAM, and it's slow because you are loading the whole data and going through the data again and again until you reach to the global minimum, meaning your overall training error is less. Stochastic gradient descent, it actually takes randomly selects one data point from the entire data set. It's very fast, but it's noisy and less stable. And mini batch gradient descent is smaller batches. Normally, you have seen this one like when you write your TensorFlow, PyTorch, or even scikit-learn based models. You sometimes use don't define it. Sometimes you define it. If you don't define it, in the back end, the batch size is always set to, by default, it is 32. So it's in 2 to the power. So 32, 64, 128, 256, and 512. It's faster, more stable, and it needs tuning for the batch sizes, meaning it depends on your data, and also this batch size is a parameter. So for getting better accuracy or better performing neural network model, sometimes we need a trial and error based method to adjust it properly, so that the overall overall neural network actually performs better. So the formula I've written it, it's very popularly known. Just so you understand, the main focus is here actually, the learning rate, meaning your parameter wt plus 1 is equal to theta or w. Actually it's the same, theta or w. It calls the name or the symbols actually attach the neural network parameters or the weights. Now, as we already know, like mini batch, why we use mini batch? Efficient computation, vectorized operations on GPUs nowadays, less noisy than stochastic gradient, more stable updates, faster than batch gradient descent, more frequent updates happen, works well with schedulers. Learning that scheduling can adapt over mini batch steps, which in the next couple of slides we will dig deeper. Now, there are different types of learning rate schedulers that are available in the literature. The first one is step decay. It decreases the learning rate by a fixed factor every k epochs or iterations. As you can see the formula, the eta t, eta 0 into lambda t and divided by k, and we take the floor. So we need an initial start, initial learning rate, and it changes based on every iteration it changes. Okay, when do we need use this step decay is like when we need like when we expect performance to improve in phases. It's simple, effective, but sometimes it abruptly the abrupt decay, the step decay, it think of it like a staircase. Okay, and this may cause instability. The next one is exponential decay. The name actually suggests there is an exponential term. So learning that next time t is equal to 0 into e to the power lambda t. It continuously decays the learning rate exponentially, and it's a smooth, it's very smooth decay over time, useful for longer time, training time, smooth and consistent reduction. Sometimes the decay too fast or too slow if you choose the hyperparameters. Let's say the initialization of your neural network is poorly done. The polynomial decay is same as previous. Instead of the exponential term, the polynomial term is here. The total number of steps t, the current step, 1 minus current step divided by the total number of steps, and the polynomial power. Normally it's 2, but it has like custom rate decay. You can control by changing the p. It's highly flexible but harder to tune because you have multiple uh, parameters that you need to tune. The next one is cosine annealing, which is like learning rate follows a cosine curve. As you can see, like previous, you have a minimum plus half into the difference, the current, the initial minus the minimum, and 1 plus cos theta. The theta is like the current iteration into pi divided by the total steps. It's good for smooth transition, later fine tuning. Very effective, widely used, but you need to know the time. The how many number of T means the total decay period, how many number of epochs or how many number of iteration that you want to, that you need to do in order to train. But the problem is like when you are training your deep neural network, you don't know like what's the optimal iteration size. Like, okay, how long you should actually iterate in order to train the, or how long the training process should go over and over until you reach the global minima. That's a bit troublesome here. The next one is cyclical learning rate. The name suggests it oscillates between a lower and the upper bound over mini batches. It's very popular and popularly used in current PyTorch TensorFlow approaches like cyclical learning rate schedulers. You directly call it, and your method will be like this method will be utilized. You can see that the next learning rate for time t is equal to the minimum, the difference, and max of 0 into 1 minus t minus c, this particular term. This particular term actually suggests like how far you have come across, and the cycles means the cycle is like 0 to 2000, 2000 to 4000, 4000 to, so these are the data points, and each batches it changes its cycle. So cycle 1 batch 1, cycle 2 batch 2, etc, etc. Am I not audible?
Yes, your voice had gone for the
Okay.
last 1 minute. Now
Oh,
it is fine.
uh,
Now it is fine.
okay, like which part? Maybe I can re-explain.
Just last 30 seconds, maybe you can.
Oh, okay.
Yes.
So the cyclical learning rate is like it's popularly also used, and it's kind of like the like benchmark that PyTorch and TensorFlow they have implemented in their library. Is like it, the learning rate actually oscillates between the lower and the upper bounds based on the mini batches. It helps to escape the local minima or the saddle points. That's our need. It doesn't require a fine-tuned LR, improves generalization, but it adds complexity because you need to have a proper selection of the n max and the n minimum, like learning rate maximum and learning rate minimum. Okay. The next one is reduced LR on Plato. As the name suggests, like reduce the training rate when performance matrices, like let's say example validation loss stops improving. Meaning, when you, let's say you are training your neural network, you pass on your training data and you add the validation split as 0.2, or you provide a validation set. If and also you add up patience, like as you can see, like if no improvement for p steps consecutively, let's say p is equal to 5, if the step is based like consecutively 5 steps, if the model's validation loss is not decreasing, the overall learning rate will decrease. It changes the learning rate by then. Otherwise, it's the same as previous. But when do you need it? When we need validation feedback is critical. Okay, it's very adaptive response to the real training signals. It doesn't need any like different parameters. It just depends on validation loss. Okay, sometimes it could be noisy and reactive to the noisy scenario, but overall as you see here, like it doesn't add much uh, parameters to tune, and that's why this is very important, and most of the time we use this one. Now let's dive into a practical implementation. I took the snippets, and these are like written in TensorFlow, as you can see, and the data that we used is MNIC. Typical approach is like xtrain, xtest. We load it, we normalize, then we like flatten, and then we prepare xtrain, ytrain. Okay. Then we define the model, neural network model. Although MNIST, it's an image, 28 cross 28 image, but we flatten from 28 cross 28 dimension 2D to 1D. That's like 1 cross 784 dimension, and that's why your dense neural network activation ReLU input shape these. And then the last layer is 10 uh, dense layer with 10 neurons, and activation is softmax, because we are in MNIST dataset we have from 0 to 9 numbers, and those will be classified. Then here we define the scheduler, like step LR, exponential LR, cosine LR, critical cyclical LR. All these, the formula that I have shown you earlier, those are implemented here. The next step is training. You pass on the scheduler name, scheduler function, and callback. Then it creates a model, it compiles, optimizes, it's taken as Adam. And the 0.1 is the initial learning rate that we considered, and the loss is categorical cross entropy, because we have we like the MNIST is multi-class classification, and our focus is on accuracy. Okay. And if you have a like a scheduler function, then callback is equal to you set. It's the like standard method to set it. And then you history, model fit, xtrain, ytrain, epochs, how many number of times it should run, the validation split, like from your training data, 20% will be cut and put into valid as a like validation set, and rest will go to the training callbacks if you have callbacks. And verbose 0 is like you want to know how like uh, the display, like the messages that it displays. As you can see here, the mini batch, like all these neural network, like when we fit all the approaches, the TensorFlow like libraries, in the backend they use mini batch approach. Okay, even though we don't set the batch size explicitly, it takes by default. It has the batch size as 32. Okay, by default. So we save all these approaches results, and then we start the and we visualize it. Okay, this is very critical. As you can see, like we have epoch and the loss. The training loss is categorical cross entropy. As you can see, the cyclical LR, it actually jumps and it's very dynamic. It oscillates a lot. Whereas, like if you see the reduced LR, learning rate on plateau, and the exponential LR, they are quite similar, and they started descending, meaning the overall loss reached to the zero. Although it's not exactly zero, but it's way closer to zero. That's why the overall, like how the learning rates or the learning rate scheduler actually has an impact on the model training, meaning reducing the loss, as you see here. Now the next one is like very important, is like the validation accuracy that we get. As you see, like the reduced LR on plateau, although like you can say like the accuracies are not that much like varied, but for this is for the demo. But in real scenario, when you develop your neural network model, please focus on these learning rate schedulers, small things, because it has huge impact on model development and overall model performance, as you can see here. Now the next is like, we until now we have explored multiple learning rate schedulers. So which one to choose when? Although I have already explained when the use cases that okay, if you have this one, this use case, then you choose this one. But let's summarize this part. When you know your training phases, use step LR. Meaning, When you know that, now we don't need exploration. So this step LR is like when you know that you need your model transition from exploration to exploitation or fine tuning, utilize step LR or step decay approach. When you want smooth and predictable decay, utilize exponential LR. Continuous reduction without sudden changes. The sudden changes actually disrupt the training momentum and it jumps from here and there. When you want to escape the local minima, utilize the cosine annealing approach. When you are certain about your scheduling, like you are uncertain about your scheduling, you don't know anything uh, here, all these step LR, exponential LR, and cosine LR, recall the term like the capital T, which is like how long you want to train your model. But in real scenario, you don't know, you don't have any idea about how long you can train, you should train your model for better performance. You have no idea. So it's always utilize this reduced. If that's the case, then reduced LR on Plato is the option, because it depends on your validation loss, like the particular performance metric that you have mentioned. It, if, and also the patience that you put, how, like how long you should wait. Okay, the performances are not at all improving, change the learning rate. Okay, for advanced optimization technique, cyclical learning rate you can utilize. It's but it has a bit uh, problem, like you have to be very uh, focused, and like the minimum and the maximum value needs to be set properly, otherwise it will be a troublesome. So the ultimate suggestion is like reduced LR on Plato utilize most of the problems, because you don't need to set those parameters. You just start from a point, value, initial value, and then it changes based on the overall network performances. Now the common pitfalls and how to avoid them. Overly aggressive learning rate decay, avoid it, because you might end up converge too early to a suboptimal solution. Insufficient learning rate decay, avoid it, because it might overshoot the optimal solution. If you don't set the learning rate properly, it will cause problems. And always remember, monitor your learning rate. So in TensorFlow you have the tensor board, which actually shows how the learning rate is changing, and you can directly see how the validation loss, your validation accuracy, training loss, and training accuracy are changing over time. Like, it's a good practice to like make it a habit. Whenever you do develop your deep learning based model, always keep like focus and keep an eye on these small things. Until this point, like before preparing this presentation, I was also like, i I did not focus much on these small steps. But now I realize like it should be a common practice, and I think everybody who are interested in who are listening to this, and also if your friends are also interested in doing these sort of stuffs, like deep learning, machine learning stuff, please recommend them that focus on these small things. Like when we get the data, without understanding the data, we directly fit into the model, and then if by best case scenario, if your model performed very well, you stop it there. You don't think your model is perfect, your model is performing on cross validation approaches, and that's done. You don't think about, let's say, if but that's a best case scenario. If you don't get the model performance properly, there are multiple ways to find out where the problem is. One such problem or one such cause could be uh, setting the proper learning rate. And how can you set it? It's monitoring it while the training phase. Now, what's the beyond? Like, I have summarized some of them, but there are plenty. It's a open research. There is no specific mathematics that tells you, okay, this is the data, because you like one learning rate method may not be optimal for all of them, may not be like applied for all the problems. So it's always like it's a trial and error based method, and it's your intuition, it's your observation capability, like, okay, something is causing this, could be this one, change it to this one. Okay, so there are many variants, and it's an open research. Those who are interested from this presentation, if you guys have like if I have influenced you to dig deeper, then you can also check these approaches. Okay, and we can even go for like combining or hybrid learning rate schedulers, because what's our objective? The main objective is like exploration and fine tuning. Okay, so we have to have a balance between exploration and fine tuning. When we explore during that time, or explore that time, the learning rate can be bigger. When we exploit, meaning when we fine tune our network, that time the learning rates should be smaller. What if, like, we know some of the learning rate schedulers, pros and cons? Maybe some of the learning rates con can be rectified by combining these two. One such example, like a ramp up scheduler followed by a cosine annealing. Let's say, like step decay and exponential error. So step decay, when we utilize the step decay, like the reason for utilizing step decay was, when you know the training phase is like transitioning from exploration to model fine tuning, then you need step decay, or like step LR approach. Similarly, when you utilize, let's say, cosine annealing, you can utilize or like step decay with cosine annealing. Cosine annealing helps you to jump out from the local minima points, saddle points. So combining these two might give better results. I don't know. I'm just brainstorming. So those who are interested, like want to dig deeper, please go through it. It's very interesting topic to discover. Now beyond the basics, it's like the research and practice. It's ongoing research. Go through it. Warm up strategies before decay phase. Learning rate test, optimal learning rate selection, if there could be some methods, architecture specific schedulers in cutting edge research, all these. Now what's the conclusion? As we already know, like the proper learning rate schedulers can dramatically enhance the training speed and model accuracy. As you already see, like the uh, reduced on LR plateau, exponential LR performed better. The overall training loss, validation loss was way more better than the other. So it has impact on overall model performance. Scheduler is crucial. Scheduler choice is also crucial. As you see, it depends. It has impact on the architecture itself and also the overall performance. If you don't know anything, you can start with reduced aileron plateau, and later on, like by observation, you can change it to different approaches, etc., based on what you need. Always monitor and adjust properly, because you should actually, it should be common practice. When you develop your model, you focus on the training behavior and tweak your schedulers accordingly. Iterate based on your problem. First, you understand the data set, your model, and your overall goals, and then you can decide, okay, this one to consider, this one to not, because you know which one like the pros and cons, and which one to be utilized when. The more understanding that you have on your data, on your model and the goal, like the selection capability will be more, and then you can decide if something can go wrong. But yeah, it's a common practice that, or if you follow all these, it's very crucial that you might end up reducing like trial and error based to a specific finding out, okay, this could be the neural network architecture, okay, this could be the learning rate scheduler, this could be the optimizers. Although the whole thing is in trial and error, but the research is still going on to find out the mathematics, how can we uh, select all these automatically. These are the references, you can go through it, all these like all the implementation, different learning rates, PyTorch based implementation and everything, you can go through it. And please feel free like to tell me, like if you have any queries, questions, you can reach out to me. And also some other topics that if like the one that I am working right now, if